let's get started. So welcome everybody. This is the British Interplanetary Society, the West Midlands branch. So in a moment, I'm going to ask my colleague Mark to say a few words and to introduce Lucas. Then Lucas will give us a talk, after which we'll have an opportunity for questions and answers. Now, I'll be moderating that. So what I'd like you to do, the way it seems to work best is if you can write that you want to ask a question in the chat, then I can pick it up and I can make sure it's done in the right order. I will ask you to ask the question if you're available. If not, I will read it out for you.
So, as you've already heard, we're going to be hearing from Lucas Beveridge from the United States today. I'll let him introduce himself in a minute. So, BIS is always, as I'm sure you've heard me say before, always looking for articles, papers for its various magazines. Here is JBIS. In fact, this is one that Lucas's article appears in. But there's the History magazine Chronicle, and there's the popular magazine Spaceflight. Excellent magazines. If you think you can offer something, please do contact headquarters or the editors. Please do join. BIS, there's lots of information on the website about different bits and pieces that we get up to. There's a monthly newsletter, and of course there's great camaraderie. And hopefully, as COVID subsides, we'll be able to meet up publicly for events in the near future. So, and as I said, please do join the British Interplanetary Society. The BIS needs you. You could do with membership. And with that, I'm going to hand over to Lucas, if I can figure out how to stop sharing my screen, that is. So with that.
So this is me. This was as he mentioned, this was a concept I came up with quite a few years ago and worked on as a side project, mostly for fun. I'm hardly an expert in supersonic or hypersonic propulsion or even air breathing propulsion of any kind, but I do have a background in rocketry, hybrid rocket propulsion. But my master's and PhD are in nuclear engineering, and my current job is working at Atomos Space in Denver, Colorado, working on nuclear electric orbital transfer vehicles and related things that I can't talk about yet. It's a lot of fun, very, very different. I had formerly worked at Los Alamos, and that's where I was when I published this paper. But yeah, anyway, I'm hardly an expert in air breathing propulsion, so go easy on me. I did my best. So I'll do a little background first for those who aren't as familiar with this. So rocket-based combined cycle engines are not a new idea. Of course, they've been around, I don't know, probably since the 1940s or 50s. I know NASA, Marquardt, and Rocketdyne did a very large study in the 60s where they looked at dozens of different permutations of rocket and air-breathing combined engines, ramjets, scramjets, all sorts of different things. But none of them have ever made it very far in development. They usually end up being extremely complex. It's one of those things, sort of like aerospike engines. It sounds really great in theory, but when you start looking into it in more detail, it's not so great. They usually end up being really heavy. You try to get the best of both worlds, but a lot of times you get the worst. And so they haven't gotten very long. I think reaction engines is probably gotten further along in development than anything else, as far as I know. Yeah, I mean, I know this is a fairly technical audience, so this is probably really basic here, but for those that aren't aware, the performance of any propulsion system, rocket or jet, usually talk about in terms of specific impulse, which is the amount of thrust you get per unit mass of propellant going out the tailpipe. So of course a jet engine would have a much higher specific impulse than a rocket because so much of the reaction mass is just air. You get it for free. You don't carry it along with you. And so you can get more delta V in theory. I suppose I never calculated the delta V of a 747. It would probably be extremely high because the specific impulse for a big turbofan is tens of thousands of seconds. So the delta V for a 747 would be enormous going around the world, but you have atmospheric drag in the way, which complicates things, so it doesn't actually keep accelerating, of course. But anyway, the whole point is that using the air as reaction mass can get you a lot more payload. So if you can accelerate through the air and get as much impulse out of the air as you can, you don't need as much rocket fuel, and you can increase your payload to orbit and maybe even get away with a single stage rocket, or vehicle, I should say, not rocket. So this is what I was thinking about. In a previous job, I used to be a design engineer for Honda. And it was not a strenuous job. I spent a lot of time daydreaming at work, and this is the kind of thing I daydreamed about. So I was imagining, I had experience with hybrid rocket motors, and was wondering if maybe there was some way you could build a really simple combined cycle engine that didn't have all the complication of the liquid hydrogen pumps and propellant, all this, the complicated stuff that would make it difficult. And so what I came up with conceptually was a hybrid rocket combined with a solid fuel ramjet, which at the time I didn't even know was already pretty well developed. Apparently they've been studied for cruise missiles and things like that. And some had flown. But I started looking at that for a long time, a little bit in the background, as a side project, like I said. So the concept really is you need to get up to high speed initially. So it would probably have to start as a rocket, or it needs a supersonic carrier vehicle to get the ramjet, or maybe even a scramjet. I don't know if you could use a scramjet with a solid fuel. One of you might know better. But in any case, you need to get up to speed so that the air breathing portion of it will work. And the air breathing portion takes over at a low Mach number and accelerates up to as high a velocity and altitude as possible, at which point the rocket motor takes over, the inlet closes, and continues accelerating into orbit. I did look at an all-solid engine as well that was like a layer cake, or a radial layer cake. I have an illustration at the end, but a layer of composite solid rocket fuel with paraffin or some other solid fuel. So you'd have an inner fuel grain that burns away, accelerates it up to supersonic velocity, at which point it reaches the layer of solid fuel, which then burns with the air through the air breathing phase, and then it reaches another layer of composite solid fuel for another rocket mode to accelerate it. But after quite a bit of modeling, I discovered that the overall performance was no better than ordinary liquid oxygen and RP1 kerosene. And so I didn't include that in the final paper. I did in an earlier draft, but I found a few errors in my initial models. So it turns out the performance really wasn't that good. But I thought I would mention it because it's still really interesting that you could build something like that. It's just a candlestick that switches back and forth between rocket and air breathing. So here's an illustration of what I eventually came up with. We have, I settled on paraffin as a fuel because it has a high regression rate.
Hello, Ange.
It works very well in a hybrid rocket because it has a low melting point. It vaporizes very quickly, and so one of the issues with hybrid rockets is typically low regression rate. A common fuel is something like HTPB, synthetic rubber, which has a high specific impulse, but it burns very slowly, or it regresses very slowly as it burns. Paraffin burns much more rapidly, so it produces higher thrust, but still has good ISP. So in this illustration, you can probably see fairly well here, there's a center burning port where the incoming air is burned. So you have really two separate regions inside the one fuel grain. You have one for where you inject liquid oxygen, and the other where the air is fed in from the inlet. So that's the basic concept. The implementation or estimating the engine performance gets extremely complicated. However, once I started getting into it more, I wanted to simply model the engine by itself, but that's not really possible. You need to have a lifting vehicle. Something I've discovered early is that you need to have a lifting vehicle, and you have to have a space plane to some extent. Even if you don't plan on landing on a runway, you have to climb gradually out of the atmosphere in order to get the most out of the air breathing phase. It can't be a pure ballistic vehicle like a normal rocket. Well, I mean, I could, but it would be kind of pointless. You're not going to get as much out of the air breathing portion of the flight. So you have to know the specific impulse at any moment during the flight. But that, of course, is going to depend on the vehicle velocity and the air density and the temperature and how much of the fuel has burned away. The thrust and regression rate is a function of the oxidizer mass flux. I'll get into that later. But it ends up getting very, very complicated. And so just to show, to give a flavor of that, down here you have the effective specific impulse and equivalent effective specific impulse. So effective specific impulse is just the ISP at any given moment. So T is thrust, D is drag, and W is weight, and theta is the pitch angle of the trajectory. So the trajectory matters, the drag, the thrust, all of this stuff has to be accounted for. And then in order to estimate the equivalent effective specific impulse, and the whole point I wanted to get at with this paper was to determine how well this engine performed. But of course you have to incorporate that with a vehicle. So, and this is why you need the integrated equivalent ISP or effective ISP with the delta V that you actually get through an actual flight, which seems a little circular to get the ISP from the actual delta V. But anyway, it requires complex numerical modeling. So there were a few complex mechanical considerations that I really wish I could have explored further, but I had to sort of hand wave some of these things. But I knew that they were solvable problems, like the variable inlet geometry for the inlet. That of course has to be necessary because you're accelerating through such a wide range of Mach numbers, like the SR-71. It's not simply a cruise missile that's launched with a rocket and cruises at one specific Mach number. And also the nozzle and the combustion chamber and all these things have to operate under two very different operating modes, two different chamber pressures, mass flow rates, temperatures, all these things, which puts a lot of constraints on the design. And this is some of those trade-offs I was talking about. Sometimes to combine the two different things, you may not end up with the best of both worlds. So I'm going to kind of step through more or less how I built my simulation code, my 2D trajectory code. Of course, you have, because of the dependence on the flight path, you have to solve the equations of motion, but you also have to solve for exhaust velocity and mass flow rate. Drag coefficient is a function of Mach number. Atmospheric density is a function of altitude, temperature, pressure. So I had to have an atmospheric model. Theta is a function of time as it goes, the exhaust. So these are all, I had to build an entire engine simulation code that models the regression rate of the fuel and the oxidizer to fuel ratio and the ISP and chamber pressure and temperature, gamma, all the fluid properties as it's burning to calculate the exhaust velocity and mass flow rate. But then mass flow rate is also a function of airspeed and so on. So it gets, this took me a long time as a side project. I was teaching myself a lot as I went along. I should mention, I started working on this project in 2013, I think. And I worked on it on and off, but I didn't actually get the final paper written until a couple of years ago. And then I finally submitted it and went through revisions. But yeah, it was educational. So anyway, yeah, the other parameters you have to worry about. So the chamber pressure is going to determine a lot of things. But the chamber pressure, at least in air breathing phase, is proportional to the stagnation pressure. But it's not equal to the stagnation pressure. It drops when it's when you're at Mach 1 or below Mach 1. You can assume it's pretty close to the same, but as the Mach number increases, the pressure recovery drops, of course. That's why ramjets don't work very well above Mach 5 or 6 or so. At that point, there's just not enough air getting into the inlet. So that's another thing that had to be incorporated into the engine burning model. Lift. So I had to hunt down sources for lift coefficients for diamond airfoils at subsonic and supersonic speeds. Actually found a really neat report from the NACA that was published in 1949. They had studied just that. They looked at diamond airfoils for different chord thicknesses and angles of attack at various Mach numbers, up to Mach 1.1 or something like that. It was a really interesting report. Drag, similar. I actually had a CFD code that I was able to use to model wave drag coefficient. It was somewhat limited. I could only model it as a cylinder with a conical nose or an ogive nose or something, and short stubby wings. But I was able to model the diamond airfoil wings, fins. And this is just the drag coefficients that I got. So the small dotted line was the simulation, and the large dotted line and solid line are my my best fit expressions that I used in the model. And then there's the atmospheric model, which determines the temperature and pressure and density of the air at any given moment as the vehicle is moving through it. They used the 1976 standard atmosphere. Pretty straightforward standard thing. The engine itself, though, was more complicated, and I had written another code previously for simulating a performance code for modeling hybrid rocket engines, and I knew how to do that. I knew that worked very well. I was able to fit experimental data that I gathered from engine tests. So I was able to incorporate that and modify it to determine the mass flow rate and the fluid properties performance of the engine at any given moment. But that also gets very complicated because it's also a function of oxidizer mass flux. So the rate that the fuel is burning away is a function of the pressure recovery and the airspeed, and it gets very complicated and ends up behaving in very non-trivial ways. Just getting these models to work correctly and making sure I didn't overlook something, and I very often overlooked a lot of things. So I did eventually get it all put together, but doing this as a side project while I was in grad school, working on other things was interesting. And here is from the eventual model that I used in the paper. This is the fuel regression rate for the air breathing phase. You can see the rate that it's burning away in meters per second. So as the port grows larger and larger as the fuel eats away, you can see how dependent it is on the atmospheric model. You can see it as it transits through different regions of the atmosphere. And there's other effects being incorporated in there. And this is a very rough illustration of the vehicle that I ended up modeling, although it's not quite right. The wings are actually a little bit smaller. It would probably end up resembling, probably more like an X-15 maybe. The wing loading would have to be really high. Like I say, I'm not an expert in aircraft design either, so I calculated the stress in the wings to make sure they wouldn't break off because the wing loading is extremely high. But I found you could do it with composites. It is possible, but it's certainly not an ideal design. Better designers could do a better job than me. I just wanted to show that the vehicle could work and what the potential performance is. So I did, as best I could, mass component breakdowns of the vehicles. I did look at an SSTO and a two-stage option. The single-stage vehicle, well, I'll get to that, but it performs okay. But there's a lot of other, a lot of masses. My referee pointed out to me that he said his quote was, "The devil's in the details." Because I had originally in my first draft, I didn't incorporate all of the component masses and vehicle mass. And he says, with these sorts of vehicles, you have all these other structures, you have wings, you've got the landing gear, you have thermal protection, it adds up. And so I did incorporate all of that. And at the end, if anyone's interested, I do have mass breakdowns for all the different vehicles. But bottom line is it still works out pretty well, at least for a two-stage, and even a single stage is okay. And like I mentioned, the wings are pretty small, so the wing loading would be really bad. I wouldn't recommend anyone design a vehicle like this for real. So here's a notional launch profile. My original idea, you'd launch this thing from the ground, of course, accelerates up through the atmosphere, but doesn't quite reach orbital velocity on its own. That would save some delta V in the vehicle, launch more payload, and then the payload circularizes its own orbit, and then the vehicle re-enters on its own, so you don't need extra OMS propellant for deorbiting or anything. And so these are some of the initial conditions. I assumed it started off at sea level. The rotational rate of the Earth is 390 meters per second, so I included that in the model as well. So 390, that was from Kennedy Space Center at that latitude. Vehicle cross-sectional area and engine inlet area. As I said, I looked at two different versions. I looked at single stage and a two-stage option. The two-stage vehicle was essentially the same as the SSTO, but it had a second. It just had a booster, had a second engine attached on top to give it more delta V. So it changed the model a bit, but includes additional TPS because I assumed the second stage would re-enter. I didn't have any illustrations of it, but I imagined the second stage would be something like a lifting body, so it could also land on a runway. And here's how it compares, the final version ended up comparing to other launch vehicles. So the two-stage version, so GLOW is a gross liftoff weight, percentage of gross liftoff weight that makes it to low Earth orbit. The two-stage version was about almost 9%. The Block 5, the Falcon 9 with booster reuse, it was kind of hard to find information, but I did find an estimate. It was about 3.8%. Single stage to orbit was 11.5%, but there's not that much payload. The Venture Star, which was the rocket, so I used a typical LACE engine, which was a liquid air cycle engine, which is probably the upper end of the performance envelope for a combined cycle engine. So I used that as an upper limit, and I used the Venture Star space plane as a lower limit because that was a rocket-based SSTO. So those are my upper and lower limits. You can see the LACE engine, although it has a 27% glow to low Earth orbit, the payload is only 4.6%. And you notice the payload for the two-stage hybrid combined cycle is about 8%, over 8%. And even the SSTO combined cycle is comparable to Falcon 9 with booster reuse, although I'm not sure if it would be competitive economically. And I didn't even begin to touch on the economics of these. So I don't know if that would actually be competitive. And that's one of my concerns with this whole thing. When I started working on this, the idea of reusable launch vehicles like the Falcon 9 was still seemed like a fantasy. By the time I finished the paper, SpaceX was reusing the boosters on the regular. So the situation has changed a lot since I started working on this. I don't know if maybe the two-stage could be made economical, but the problem, like with any solid or hybrid, is it makes it hard to reuse them. You'd have to take the whole thing apart. You can't just refuel it. You have to take it apart, clean it, stick in a new fuel grain, check everything out, put it back together. So I don't know if something like this would be really competitive, but the performance is not that bad. Like I say, the SSTO, maybe because it's only a single stage, you could make that competitive with Falcon 9. I don't know. So that's all I had in the PowerPoint. I'm probably forgetting details. So yeah, I'm ready for questions now. I'm sure there's a few.
Oh, thank you, Lucas. That was a great talk. Yeah, I knew it would be pitched right for the engineers in the audience. So I think thank you so much for that.
Yeah.
Right. Let's have a look. See what we got. Okay. Questions? Anyone? Okay, Mark, I'm going to pick on you first. Yeah, go for it.
Lucas, did you look at charge stress at all? Paraffin wax is not a particularly strong, not a particularly good engineering material, and I've had bitter experience of solid propellant rocket motors with charge breakup. Yeah, did you look at any charge stresses at all?
No, there's a lot of details like that I had to just hand wave past and say, well, okay, you'd probably have some webbing in the fuel grain, to support it or something like that.
Uh-huh.
But it would be necessary. Something else I thought about, but I didn't put in the illustration, is you might have a partition between the section of the fuel grain that's air breathing and the section that's rocket breathing. Just to prevent one from bleeding into the other or consuming too much of the other. You want to the air breathing phase to eat up too much of the rocket propellant and then not have enough left over to reach orbit.
Okay.
Something like that.
Did I understand you correctly that the you modelled the performance with a continuously variable throat?
No, it was a constant throat.
It's a constant throat, right?
Yeah.
Did you consider the idea of a CVT with a configured for aerospike?
I thought about it, but I decided it was too complicated. It was beyond the scope of what I was trying to do. I just wanted to show and introduce the concept and say, okay, here's a potential thing. That might be an interesting follow-up.
Would help with the efficiency of the hybrid and the ramjet. So
yeah,
interesting.
Yeah, because the nozzle is one of the big constraints there with the two modes.
Thank you.
Yeah.
I'll let somebody else have a go.
Okay, next up is Rich. Rich R. Do you want to ask your question? Unmute yourself. Okay, I'll ask it. So Rich is asking, he said on slide 14 side view, it might seem that the structure would have a large angle of incidence to fly straight. He says it might just use body or cylinder. Not quite sure. What do you mean there?
Oh, I see. So using the fuselage itself to produce lift instead. Is that correct?
Yes, I think that's what you mean.
Yeah.
Yeah.
That's a possibility. I didn't model that. I didn't use any CFD codes to estimate the lift around the fuselage, but that could be, I mean, the wings are small enough, you might be able to get away with that and just maybe widen it or a little bit, change the shape a bit so it produces lift on its own, and then you don't need the wings. Because you really just need the lift during the ascent phase to help the trajectory. So that's a possibility. I didn't look at that though.
The other thing he said was that the thrust line would also result in a large angle of attack.
Oh yeah. So yeah, you might rearrange the engine. You might have two smaller engines or something closer to, on either side instead of above.
Okay, great, thanks. Right, next question is, oops, bear with me. So Michael Richardson asks, actually he's got a couple of questions. He said, would it take off horizontally or vertically?
That's a good question. So the takeoff speed would have to be really high with those small wings. So you would have to take off maybe off a ramp or a rail or something. I had originally assumed it would take off from a runway, but the takeoff velocity is 0.6 Mach or something like that because it's so heavy. So it's somewhere in between is the answer. At least for this vehicle, a better engineer might come up with something that could take off from a runway.
Michael suggests, what about a railgun? Yeah. Darryl, how do you think the engine would compare to Reaction Engine's engine?
Theirs is probably a lot better, especially since it can be refueled easily on the flight line, and it can take off from a runway. The one thing I did find I forgot to mention during the presentation is that liquid hydrogen is used as propellant in most of these things, like the Venture Star and LACE engines, and the low density requires giant tanks and insulation and additional structure and all these other things, and that was a big part of the reason. It took me a while after I got those simulation results. I'm like, this doesn't make any sense. It should be worse than this. But then I thought about it. No, the fuel is a lot denser, so everything's smaller, and so it ends up being a big effect. So in that regard, reaction engines may not be as good because they have big liquid hydrogen tanks, but in pretty much any other regard, I think it's probably superior. They're so far along in development now. I think they're doing pretty well.
Yeah.
I think another way to think of this, although we're space types, having worked on missile propulsion, potentially this type of engine could be of interest for hypersonic missiles with a change in oxidizer and a change in the fuel. The basic concept could be very interesting in terms of hypersonic interceptors for the military.
That could be. It's funny. At the time when I submitted this, I was working at Los Alamos, and you have to submit any paper you're going to publish to the export control and classification people to make sure it's okay. There's nobody at Landell that works on that kind of stuff, but they went to the head classification guy. He signed off on it. So it's like, okay, yeah, you're fine. Go ahead and publish it. All right. I'm not going to argue.
Yeah, so. Britain's in a funny position. Back in the 90s, the government scrapped our ability to make very large rocket motors. And now we are in the unenviable position of wanting to do hypersonics, but we don't have, we could put in, it could be built and put in, but there is no existing capability for large rocket motors, large solid propellant rocket motors. So this type of system design could be of interest. It's interesting.
The other thing that they scrapped, Mark, was the Department of Security. So you couldn't say it.
You seem to be having a lot of people are starting to join us this late. Maybe they've dropped off. Right. Neil and Roz, I'm not quite sure which one is asking, but they're asking what was the LEO payload capacity and what sort of satellites could be launched?
So what are the actual masses? Let me see. I have the mass breakdowns here.
You had the glow there, didn't you?
Yeah. I had the percentages. The liftoff mass was almost 400 metric tons. So it's in the same category as Falcon 9 or Delta 4 for either one of them. So the payload mass for the two-stage vehicle was 26,700 kilograms, and the single stage was 10,800.
Mm-hmm. And Rich makes a comment about whether it's scalable.
I don't know. It seems like it would be hard to scale up much more than that, but I don't know. There's an issue with hybrid rocket engines. Nobody's ever built one more than, I think, 500,000 pounds of thrust. And there's combustion instability issues. So that's another thing that would have to be dealt with.
Okay. Any more questions? Either attract my attention or write something in the chat. I'll pick it up. Okay, well, I'll assume that's it for today. So I'd like to say a big thank you to, oh my goodness, just as I start to do that for the second time, Neil and Roz, are there any plans for our commercial interest? Oh no, you missed that bit. No, it's yeah. He's asking if there's any commercial interest in its use.
I don't know. I mean, you're the first people who have shown any interest at all.
Well, if the military are watching, given what I've just said.
Yeah, they'd have a hard time keeping it classified now that the head of classification at Los Alamos gave it the all clear. So
interesting stuff. interested.
Okay, so this time, no one interrupt me. I'd like to say thank you to Lucas Beveridge for a great talk. It was great for you to share your research with us and the paper. I didn't actually get to read it before, but I know Mark went through your paper on JBIS, and yep, he's got it there, yeah, as evidence. So this is a highly unusual meeting for us, of course, because it's in the evening, so that we can actually get you available. So a 10 a.m. start for you in Denver, Colorado. So we very much appreciate you giving up your Saturday morning for us. So thank you very much.
Thank you very much, Lucas.
It was my pleasure.
Thank you, Lucas.